Hello everyone, welcome to AIT Tech Talk. My name is Narala Siddhartha. My roll number is 20951A6744. My branch is Computer Science Engineering with Data Science as specialization. My subject is Business Economics and Financial Analysis. Today my topic is a cost of production model for Bitcoin. So let's start. So I mainly divided the content into four parts. The first part is going to be about the introduction about the Bitcoin and its mining. In the second part, we are going to discuss about the discussion to mine and the cost of production. The third part is a basic discussion and the fourth part is the conclusion. So let's start. Introduction. The basic idea about the cost of production model for Bitcoin. So introduction. So what is Bitcoin? There are three primary ways one can obtain bitcoins. The most popular and widely accepted of the so-called is cryptocurrencies. The first way to is to buy them directly from another individual or via an online marketplace in exchange for national fiat currencies or other cryptocurrencies. The second way is to accept them as payment for goods and services or as wages. The third is to mine for bitcoins using computer hardware and software specifically designed to solve the cryptography algorithm algorithm underlying the Bitcoin protocol, thus producing new bitcoins. The decision to mine for Bitcoin comes down to profitability. A rational agent would not undertake production of bitcoins if they incurred a real loss in doing so. Bitcoin mining employs computational effort measured in gigahashes per second. The hash rate or number of hashes per second can be thought of as somewhat analogous to the cycles per second, which is also known as hertz, of computer processors. This computational effort is directed at mining Bitcoin in competition with many other miners who presumably are also motivated by profit on average. The more powerful the mining effort, the more likely it is to be successfully mine bitcoins during a given interval. The success in finding bitcoins depends not only on hashing power but also on the difficulty level of the algorithm at the time that mining is undertaken. The difficulty specifies how hard it is to find a bitcoin during some interval. The higher the difficulty, the more computational effort will be required to mine bitcoins at the same rate as with a lower difficulty setting. The Bitcoin network automatically adjusts the difficulty variable so that one block of bitcoins is found on average every 10 minutes. As more aggregate computational effort is added to mining bitcoins, the time between blocks will tend to decrease below 10 minutes, the result being that the network will adjust the difficulty upwards to maintain the set 10-minute interval accommodating the excess mining effort. Likewise, if mining effort is removed from the network, the length between blocks would grow longer than 10 minutes and the network will adjust the difficulty downwards to restore the 10-minute interval. Each unit of mining effort has a fixed sunk cost involved in the purchase, transportation and installation of the mining hardware. It is also a variable or ongoing cost which is the direct expense of electricity consumption. Each unit of hashing power consumes a specific amount of electricity based on its efficiency, which has a real world cost for the miner. Because miners cannot generally pay for their electricity cost in Bitcoin, they must refer to the currency price of a Bitcoin to measure profitability given in a monetary cost of electricity. It seems to be the case that the marginal cost of Bitcoin production matters in value information. Instead of approaching Bitcoin as a digital money or currency, it is perhaps more appropriate to consider it a virtual commodity with a competitive market of producers. So the second one is the discussion to mine and the cost of production. The objective discussion to mine for bitcoins can be modeled. The necessary inputs are the dollar price of electricity, the energy consumption per unit of mining power, the dollar price of bitcoins, and the expected production of bitcoins per day, which is based in part on the mining difficulty. Hayes 2015 applied a model for determining the expected number of cryptocurrency coins to be mined per day on average given the difficulty and block reward. Number of coins issued per successful mining attempt per unit of hashing power. Bitcoin per day is given by beta into rho by sigma into 232 seconds per seconds hour and hours day, where BTC per day is the expected amount of bitcoins a miner can expect to earn per day. Beta is the block reward, rho is the hashing power employed by a miner, and sigma is the difficulty. The constant SCCHR is the number of seconds in an hour, 3600. The constant HR day is the number of hours in a day, 24. The constant 232 is the normalized probability of a single hash solving a block and is a function of the Bitcoin algorithm. The value for rho for the purposes of this paper will be given at a standard unit of 1000 gigahashes per second of mining power, or it is equivalent to 1 terahash per second. So rho is equals to 1000 into 109. The block reward for Bitcoin is given at 25 Bitcoins per block currently. The constants which normalize the dimensional space for daytime and for the mining algorithm can be summarized by the term theta, which will equal to the marginal product of mining should theoretically equal its marginal cost in a competitive market, which should also equal its selling price. Because of this theoretical equivalence, and since cost per day is expressed in dollar per day, and Bitcoin and production in BTC per day, and dollar per BTC price level is simply the ratio of cost per day by Bitcoin traded per day. This objective price of production level P star serves as a logical power bound for the marketplace, below which a miner would operate at a marginal loss and presumably remove themselves from the network. P star is expressed in dollars per Bitcoin given the difficulty and cost of production. P star is equal to E day by BTC by day star. So let's discuss about some. These equations are useful in application as well as in theory. It informs miners objectively as to which price they should undertake or else giving up mining. It also informs miners when to stop or start mining given changes in difficulty and electricity costs. Furthermore, looking at marketplace places for a given difficulty and known average electricity costs, the average energy efficiency of mining for the entire network can be imputed. It is useful to consider a hypothetical example. Assume that the average electricity cost for the world is 11.5 cents per kilowatt hour and the average energy efficiency of ESIC mining hardware currently deployed is 0.95 joules per gigahertz. The average cost per day for a 1000 GHS mining rig would be $2.6 to $2.622 per day. The number of bitcoins that 1000 GHS of mining power can find in a day with difficulty of 0.010604 BTC per day. If the market price were to drop because below that value, miners would be operating at a marginal loss and halt production. Continuing the analysis of this example, if the difficulty were to increase to greater than the given amount, holding all these else constants, miners would cease operations. Also, in this example, and holding all else constraint, miners would cease operations if their energy cost rose to more than 13.952 cents per kilowatt hour. Likewise, a miner would cease operations if their mining hardware consumed energy at an efficiency worse than 1.15 watt per GHS. As real world mining efficiency increases, which is likely result of competition, the break even price for the Bitcoin producers will tend to decrease. Today, the ASIC mining rigs are available for purchase having somewhere around 0.50 to 0.60 watts per GHS energy efficiency. The average energy efficiency right now across the mining network, which is the value which regulates the marginal cost, seems to be around 0.90 to 1.00 watts per GHS. So, the conclusion: technological progress has already brought down the cost of mining by orders of magnitude. The irony is that a competition to produce bitcoins induces more and more technological progress to increase efficiency and create competitive advantages. It might also serve to reduce the marketplace of Bitcoin. The difficulty adjustment mechanism serves to stabilize the predicted decrease in production cost and having of the block reward, which will do the same. Of course, subjective factors will also confer value and be expressed in the marketplace. Speculators and miners who hold all or part of their production are one example. These so-called Bitcoin 2.0 applications rely on the validation work of miners to secure non-Bitcoin transactions and may prove to be more valuable than Bitcoin in and of itself. Thank you.